Hello and welcome back to another video with It's Dr. Dan, and today we're going to be practicing equilibrium problems. The big idea here is we're going to be putting together all the different concepts that really get covered in terms of introductory chemistry when you're learning the basics behind equilibrium. So this is going to be mainly a practice problem video putting together all those major concepts so that way you can learn how to work through all the different types of problems that you'll see. So in putting all this together, well, what does it all entail? Well, the first thing is when you learned about equilibrium is that there's this forward and reverse reaction. And when the rates of the two sides of the reaction become equal, equilibrium is achieved. Now, behind all that, what essentially governed that entire process was the whole idea that collisions had to be made and molecules had to be oriented the right way. And there had to be activation energy that was required for these different reactions to happen. So you kind of learn that, okay, concentration, temperature, depending on how much energy there is, the pressure, the volume, all these conditions play a role, which is where we were really seeing that, okay, well, we can essentially poke this metaphorical equilibrium beast with a stick and see like, all right, how is it exactly going to react to that? And then we also learned about all the different acids and bases and how the different strengths play a big role behind all that as well. Now, when we learn about all that, that all kind of gets put together into this concept of the K expression, which is an equilibrium expression, where if you have a balanced chemical reaction, you can write it as a K expression where you just put the products over the reactants, and it can be used to describe how the system will behave at equilibrium. Will the reaction favor by creating more products? Or will it favor creating more reactants? And that's what we're going to be diving into during this video by going through all these different practice problems. So let's dive into it. We're going to go through some of the important things to remember before we do. And we're going to be going through a range of different problems from very easy to very hard. So that way you can get a big idea. And if you're looking for a specific problem, feel free to use the little chapter markers in the description or below the video to be able to help you navigate the entire process. Okay, let's go take a look. All right, the first thing that we have to remember before we start is this concept of products over reactants. So whenever we have the products over the reactants, what that entails is that we are writing essentially the concentration of each of the products, and we're going to be raising them to their powers of which is their coefficients, right? So if I have, let's say C, for example, and it has the coefficient as little c, we'd raise it up as a power. Same thing with D, and then with the little d, with the lowercase d to help represent that as well. We would do the same thing for the reactants, right? We would put them into square brackets, which just as a reminder represented concentration in the form of molarity. And then we would also apply their coefficients to tell us what power we raise it to, because concentration plays a big role in how all this gets changed. Now, depending on what the K value is, this is something that can either be calculated if you know all the concentrations, or it is something that is given to you. Now, depending on what the size is, it tells a story. If K is greater than 1, then that means it's going to be favoring the products. If K is less than 1, it favors the reactants. So when we refer to products, this is usually saying, hey, this is going to shift towards the right-hand side of the reaction. And if we refer to it as reactants, that's going to favor the left. Now from there, if you can also have K is in the middle where it's equal to 1. This is when the concentrations are equal to each other. This is a very, very rare situation, but it is possible for this to happen too. Now, the other thing to keep in mind is when it comes to K, you're going to see all these little subscripts describing what type of K you have. We essentially treat them all relatively the same, but it can give you a little bit of a snapshot of what the problem is referring to, especially if you're thinking about acids and bases or maybe with water. It gives you an idea of really what kind of problem you have. So it is helpful to kind of remember at least the ones that pertain to your course. So for people who are watching this for introductory chemistry, I'll mark them for my course. But if you're looking for other ones for your class, if you're another student, then you have to try to make sure you verify that with your teacher. So for here, there's a big list of them, right? So the first thing that we generally start with is KEQ, which is referring to EQ is equilibrium. This is usually the most generic form of it. So for my course, this is usually one of the most standard ways that we show this. So with this one, we'll put a little star next to it to tell us, hey, this is pretty normal. The next one is Kc, which is referring to concentration. This is also a pretty normal one because we're always dealing with molarity. Kw is with water dissociation. When it comes to acids and bases, this one is very, very normal as well. There's Ka and Kb, which are acids and bases. Both of these are typically used when we're referring to that as well. Now with solubility product, this one is hit or miss for introductory chemistry. It depends on your teacher. So for this one, if you're talking about net ionic equations and you have to write it as an equilibrium constant, then it is pretty normal to represent this. We will go through a couple examples in this video too. Now the last two are pressure or equilibrium via pressure and equilibrium of formation. These two typically you only see in General Chemistry 1 or General Chemistry 2, which is when you go into like really advanced equilibrium problems. These will not be covered in this video. So if you were coming here to look for this, then, keep on moving, unfortunately, with that particular part. Let's look into some other things that we need to remember as well. The last thing was Le Chatelier's principle. So we'll also be predicting how can these different reactions shift. So if we increase the concentration or the temperature, pressure, volume, or even add an enzyme, if I want to poke the reaction with a stick, what exactly is going to happen as a result? So that's going to be our last little thing. So let's go look at our first problems and go through all the different practice and see exactly how we will conquer these problems. So for the first example, one of the most common problems you will get is it says consider the reaction, and then it asks you to write the equilibrium expression. So we have disulfur hexafluoride is going to be reacting to making sulfur fluoride and then fluorine gas. So when these are made, what we're going to be doing is we will take our products and put it over our reactants. So being like a SF6 on the right hand side, notice how it has a power of 2. So for its coefficient, so we are going to put that outside of the brackets. And then we have fluorine on the right hand side too. That one does not have a coefficient, so we do not need to write it. And then we have our reactants as well. So it's S2F6, and we will put that inside of brackets. And then this entire thing is going to be equal to KEQ, which is what we were trying to solve in the problem. Now, when you have this expression, one of the most common types of things that you will have to do is use it to try to define and to work around how the formula exactly works. So for this particular problem, what we are going to be doing is using the expression calculate KEQ using the following concentrations. Now, the thing about this is one of the things that's very frustrating about these problems is very easy to accidentally get the formula incorrect. So you want to make sure you double check your work. Remember, solids and liquids are never included in that formula. The other thing is you want to make sure you have your powers being used properly as well. That's also a very common error for many of these problems. So what we're going to do is we're just going to plug all these concentrations in. So the first one is SF6, which I actually miswrote. I should have said SF2 by mistake. So let's fix that in our problem. So this is SF2. So let's plug that formula in. So that was 2 molar, and that is going to be to a power of 2. And then we have fluorine, which is also 2 molar, and that is to a power of 1. And then what we are going to do is divide all of this by 1 molar, and that is to a power of 1 as well. Now, when we put all this into our calculators, this is going to be solving for KEQ. Now, so when we're doing these different numbers, it's really easy for it to it allows you to kind of predict which way it's going to go. And then you can also do Le Chatelier's too. So with this answer, we get an answer of 8 for our problem. So we're going to write that down. So with this type of problem, what this can essentially tell us to do is we can kind of determine a little bit more about this. So one thing about it is like, well, based on that KEQ, are there more reactants, products, or an equal amount at equilibrium? So this is where it's important to remember your K trends. This is a very common question that's typically put on equilibrium exams, especially on final exams that may contain equilibrium problems. So the one thing you got to remember is, well, it's all about K, or which direction does it go? Is it greater than or less than 1? In this case, we have a K that is equal to 8. So that's a lot greater than 1. So what that's going to tell us is that this particular reaction is going to be favoring the products. All right, so it's going to be going towards the right-hand side of the reaction. So you're going to have more products in your end reaction at equilibrium. Now, the last thing that I asked is, well, let's think about Le Chatelier's principle. If fluorine is removed, what would happen? Well, so Le Chatelier's principle is all about trying to think, how is the system going to react? So if we remove fluorine, the system is going to freak out because all of a sudden all the fluorine is missing. So it's like, well, if you kind of all of a sudden, I don't know, maybe this might be a little too real, but you look in your bank account and all the money's gone, you're going to freak out. Well, what are you going to do? Well, you're going to try to earn more. So how are you going to try to do that, right, and try to earn more? Well, the entire reaction is going to tip in the direction towards fluorine, meaning that we're going to be favoring that right hand of the reaction even more heavily because it's going to want to generate more as a result. One thing that, if you can kind of remember, if we take something away, we're going to shift towards it, right? So if you take, you shift towards. So in this case, it's going to be shifting to the right, or in this case, towards the products to help create more fluorine as a result. And you can kind of analyze that too regarding the other species, what would happen. So that's another common question is, well, what would happen to the SF2 concentration? Well, being that fluorine went down, as a result, afterwards, SF2 would go up. In terms of S2F6, that one would decrease because more reactants are turning into products. So it depends on how the problem is worded. You got to think, well, what would happen after equilibrium is re-achieved after the problem? Let's go take a look at another example. So in our next example, we're going to be practicing writing more equilibrium expressions, but we're going to be essentially reusing a lot of the rules that was covered in my equilibrium video, which one of the things is that we only include gases and aqueous substances when we're talking about equilibrium. Solids and liquids generally are never included in most equilibrium expressions, being that essentially this is all about how molecules are going to be moving around, and it's generally more free. And we're generally also talking about very, very small concentrations as well. So liquids are generally too concentrated, and then solids are a little bit more complicated to actually explain with these principles. So we're only ever referring to aqueous and gases. So the first thing is, when we look at this first problem, you want to look at what all the phases are. So we have SiH4 plus 2Cl2 plus SiCl4 plus 2H2. And the thing is that you'll notice with all of them is that all of them are gases. So what we can do is we can write this problem just like normal. So on the right hand, so we always do products first. So we would write SiCl4 as a product, being that it doesn't have a coefficient, that would be to the power of 1. Then we have H2, that has a coefficient of 2. So what we would end up doing is making sure that is to the power of 2. Then from there, we put everything with the reactants. So we have SiH4 to the power of 1. And then we would do Cl2 to the power of 2 because its coefficient is a 2 in the front. Not the subscript, but the coefficient in this case. So that is how we would write a proper equilibrium expression. Now, if we were to go to the next one, which is PCl5, turns into PCl3 and Cl2, we want to check to make sure everything's balanced. But the one thing is that you might notice is that, well, we have a liquid in the problem. So what that means is we're not going to end up including it in our KEQ. So we'll still do products over reactants. So we have Cl2, and then we want to put that all over the reactants, which is going to be PCl5. So that will be down in the denominator, so PCl5. And being that that does not have a power, this would be the correct equilibrium expression. Now for the next one, we have FeO, that's a solid, plus CO gas, and FeS. So what we're going to be doing here is once again checking all the phases. So you see that we have a solid and then another solid, so we're not going to include those, only the gases. So when we write this, we do products over reactants. So we have CO2 to the power 1 all over CO. And you're going to see like, oh, these are pretty easy, right? It's just all about products over reactants. Say that to yourself. Products over reactants, products over reactants. That's something that's going to kind of stay home for a lot of different points in chemistry, especially if you have to take Gen Chem 1 or Gen Chem 2 as either a chemistry or biology major. You're going to see that pop up in different sections of the class. All right, now the last one, what we have is, once again, we're looking for all the different phases. So one thing that we can see is that, oh, we have a solid here. So we're not going to include that. So when we do products, we have KNO3. And one thing that we can kind of notice is that it has a 2 coefficient. So we'll put a power of 2 in front of it. Then we do our reactants. So we have PbNO3. And that's going to be 2, that's a subscript of 2 outside of brackets. And then we have our KCl. So we'll put that in another color just to help emphasize it. And that's to a power of 2 because of the coefficient on the left-hand side. Okay, so we want to make sure that we kind of follow along with all these, plugging them all in. Remember, products over reactants, place your powers. So it's just putting your coefficients as powers, and this is how we do these kinds of problems. Let's go on to our next type of problem. So one of the very common problems is doing Le Chatelier's principle. And this is something that usually you have to memorize the different trends unless you're able to kind of visualize how the reactions shift forward and reverse. If you're planning on being a chemist or a biologist, I would recommend remembering the trends because it does help you be able to predict and understand how chemical reactions occur. But if you're just trying to get through your course, then at least knowing them till you get to the end of your exam. But a lot of them kind of follow some common sense kind of things about how reactions work. The more you kind of realize of how it relates to your actual world around you. So one of the things is, well, what direction would equilibrium shift for the following changes in this endothermic reaction? Okay, so it's being told what kind of reaction we have. So being that it says that it's endothermic, one thing that you have to remember is, well, where do you place heat? Is heat being absorbed or is it released? Endo is a positive value. It's something that is being absorbed. So what you would do is, this is going to be a reactant on the left-hand side. If it was exo, then it would be written as a product on the right-hand side. Could affect how you would list some of these different values and how they would change. So the first one is, well, if carbon monoxide is removed, what would occur? So if I remove CO, well, which direction is the reaction going to shift? Well, it's going to panic and realize that, oh, all of this is missing. So it's going to end up shifting towards the right to create more CO as a result. So with this one, we would shift towards the products as a result. If I go to the next one, which is, what if temperature is decreased? What would exactly happen in that result? Well, temperature, the way that we treat it, it's very similar to a concentration. If the reaction's getting really, really cold, it's going to be like, well, what do I do? Well, if you get really cold in real life, well, what's the first thing you do? You either add more layers, turn up the heat, you do something to warm yourself up, right? That common sense of what do you do in everyday life? So if that were to happen, we would shift the reaction in response to the reactant side. So we will shift it the other way. So reactants, and we would try to heat ourselves up by making more reactants. Now, what if carbon was removed? So carbon, if you can see right here on the left-hand side, notice how carbon is there. So what if I remove it? Do I follow the same trend I did before, where if I take something away, I shift towards it? But notice one thing next to it, right? It is a solid. Ooh. So what does that mean? Well, if you remember, how would you write the K expression? Well, would you include a solid in your final expression? And the one thing you can remember is you don't. So would it have a change? In this case, no, there would be no effect. So if you have a solid or a liquid, it doesn't do anything. So that's one thing to remember, right? It's less work for us for later. All right, now what if pressure is increased? All right, when it comes to pressure, the thing that we have to do is we got to look at the number of moles on the different sides of the reaction. So if we want to increase pressure, what it's going to do, it's going to shift away from more moles of gas. So one thing that we see is if you look on the right-hand side, we have 3 moles of gas. So we have the 2 moles of CO, 1 mole of CO2. So there's 3 total. On the left-hand side, well, there is 0 moles of gas. So which way could it go to relieve pressure? And that way, where could you go? Where's it less crowded? On the left-hand side, on the right-hand side. And one thing that you'll notice is that, well, if I end up shifting this to the left, then it's going to be a lot less crowded. So we're going to be shifting it towards the reactants if we increased the pressure. All right. Now that's how we look at Le Chatelier's principle. Let's go take a look at our next example. Consider the following example. So if I have 2SO2 and it's reacting with oxygen gas to make sulfur trioxide, and I have a K that's equal to 680. Now from that, if at equilibrium, we have the concentration of SO2, which is 0.300 molar, oxygen, which is 0.150 molar, and I ask, what is the concentration of SO3? How would you do that? Well, for this particular problem, if you need to find a concentration of an individual species, you need to rearrange the problem. You need to create your K expression and then rearrange it. So the first thing is, if I want to set up my expression, well, you know that 680 is equal to K, and then it's going to be equal to the products over the reactants. So we have SO3, which is what we want, and all of that is going to be over SO2, which is to the second power, and then also oxygen. Okay. So now with that, what we're going to do is we're going to rearrange the equation. So that way we essentially get everything by itself. You could kind of plug everything into it right off the bat if you really chose to, but it's usually whenever you're doing this problem, it's sometimes helpful to just kind of rearrange it so you can kind of see how to use it. So when you're rearranging this, one thing that you would do is we'd have 680 on the left-hand side, and then we would want to essentially multiply both sides by the denominator. So if I were to do that, where I multiply the right-hand side by the denominator, so that way they'll cancel, we'll multiply the 680 as well, so that way it gets rearranged. And as a result, you'll see that the bottom cancels. And then what that's all going to be equal to is SO3 squared. So we almost have SO3 by itself. So what's the last little thing that you have to do? How do you remove a square? Well, the opposite of a square is a square root, right? So what we're going to do is we will square root both sides. And what you can see is this formula that we kind of came up with on the right-hand side is going to be equal to SO3 as a concentration. So now what we are going to do is we're going to plug all of our numbers in. So what we had, right, we had 680, then our concentration of SO2 was 0.300, we'll square that, and then times oxygen, which was 0.150 molar. So when we plug all those values in, what we are going to get as a final answer is going to be 3.0298 molar. And then we would round that to 3 sig figs, which would be 3.03 molar. Okay, so that's how you would solve for a concentration. I would recommend trying it on your own just so you can try to rearrange it yourself. It's, it takes a little bit of algebra, but sometimes you will have to do this. This is a very common thing to have to do when it comes to pH problems, because you're usually solving for maybe the hydronium or the hydrogen concentration or the hydroxide concentration, which you could then convert to pH or POH and all those different species as well. So let's take a look at our next example. So for the next one, which is all about solubility products, and I ask you write the net ionic equation, then the KSP. So if you have to define a solubility product, it's all about how does it dissolve in solution. So the first thing is, well, defining what is led to iodide. So when you see the Roman numerals, the first thing for you to get out of your head is thinking that this is a subscript. A lot of students that I see think that that is a subscript, but that's telling you what the variable charge is. So being that is lead next to an iodine, we will swap drop so that that charge of 2 will get traded down. and then that one is going to get traded down on the other side. So what we will end up having is lead I2 as our final structure. And what we are going to be curious about is, well, how is that going to dissolve, or if it can even dissolve? One thing is that you'll notice is that lead iodide is actually very, very insoluble. It's generally considered to be a solid, but it can still, even though something is labeled as insoluble, it still can break down into its ions. It just usually has a very, very small K value. So the way that we would represent the dissociation equation is we would write lead 2, and then we would reset the ions. So being that we have I2, we don't just write I2 like this. That's a no-no. The 2 would actually get brought in front because it's like taking lead iodine and then smashing it into a million pieces. So what exactly would happen when you break it? It's going to go into all of its ions. So being that these are both in solution, they are considered to be aqueous. So what we would do is our products over reactants. So you will quickly see that the KSP is only equal to the products because our reactant is insoluble in this situation. Okay, so we would write it just like this. Now the thing is, how do you interpret these different K values? What they're telling you is how soluble something is. So the bigger the K value, the more soluble. So let's say if I had the KSP for a bunch of different salts. So I have lead sulfate, aluminum phosphate, silver chloride, and then I have their respective Ks. So how do we choose? Well, whichever one is the biggest would be your most soluble. So when you kind of look through these, well, you see lead sulfate has the biggest number out of all these. So this would be your most soluble. Whereas aluminum phosphate would be your least soluble because it's your tiniest number. So this would be your answer here, right? Is this top choice? Let's go on to our next example. So for our last example, what we are going to be doing is writing the Ka for the following acid. So it's very common that you will have to write Ka expressions or even Kb expressions for general chemistry. So one of the things that we will do is when we are writing these, we typically are writing how they would react with water. So if I have HiO3 and it's reacting with water, well, the first thing is you have to label the acid and the base because that determines how they are going to behave, right? Acids donate protons. So what's going to happen is the H from the iodic acid is going to donate to water. So when we write that, we are going to write our IO3 minus and then our H3O plus for our other expression, right? Or sorry, for our other product. So now that we have that, what we are going to now do is write our Ka, which is products over reactants. So being that the only thing here is that we don't include is water, because that is a liquid, the rest of these would all be considered aqueous, being that they're ions and that they're soluble in a mixture. So we would write our products all over our reactants. Okay, so we have IO3 minus, HO3 plus, all over HiO3 as our final piece. Okay, and that's how we'd write Ka and Kb. Now, the last thing is sometimes you have to interpret the strength of an acid or base. So depending on what the size of your Ka value is, determines the strength, just like we did with KSP. The larger the number, the more ions that are being generated in the solution. The more ions, the stronger it is. So the stronger the electrolyte, the stronger the acid, the stronger the base. And you can also do equilibrium problems with these too, where it comes to Le Chatelier's principle. We're just determining how acids and bases behave with figuring out pH or pOH. All right. So this has been my summary of all the major problems that you generally will see in terms of equilibrium. This is obviously not all of them, but it's more practice to help you master them and to go through them. So thank you so much for listening. If this helped you, please let me know. Please reach out to me with any questions. Feel free to either email me, message me, or if you're just watching the video on YouTube, you can comment below with questions. But thank you so much for that, and I really appreciate that. And if this is your first time here, please hit that like and subscribe button. And if it did help you, please watch my other videos. They're all here to help students just like you. This has been Dr. Dan here, and thank you so much for listening and trying to learn a little bit about chemistry. I'll see you all later now. Bye now.